screening, all right? I will say, if you haven't, definitely read the Batchnik and Fidel chapter on this screening. It will change your life. It's one of the best chapters, statistical chapters from a stat book I've ever read. It just does a very, very nice job of systematically walking through different types of things that you should be thinking about in terms of a general multivariate screening. Now, the procedures that we're going to go through today aren't for specific tests. As we go through, we start sort of looking at regression or sort of different types of analyses. There'll be different types of things that you will want to key in on and take a look at and things like that. This would just be, hey, I've got some data. I'm planning on running a number of different analyses within this. I just want to generally see, do my data meet the assumptions of multivariate analyses types of stuff, okay? So we're going to go through general things, then when we get into regression, there'll be some other things that we need to add on specifically for that analysis, but this is just kind of a general overall screening. But this is all, 90% of this is taken from Batchnik and Fidel. That chapter is very nice. I would strongly encourage you to go through, read it, take notes on it, and if you do that, you're going to be a rock star. All this stuff will make sense. You just knock these out, no problem. Okay. So, who likes haikus? Right? This is fun. No one likes my stat haiku. Think on it a bit. It's fun. All right. So a lot of this is going to be review of some stuff that we did last semester. But thinking about why we go through and screen data, why this is important. One, all the analyses that we run are predicated on certain assumptions. If this happens, then the results that you're going to get from this analysis will be sort of reasonable. But as soon as we start violating these assumptions, I don't know, we've changed the rules of the game, right? I just say, again, sports analogy, is this team better than this team? Well, if we're all playing by the same rules, I can go through and say this team's better than that team, but all of a sudden if I've got 15 men on the field and sort of the goals are different, and all of a sudden it changes all my assumptions, and I don't know any longer sort of if I can trust the results of the analyses that I'm getting, right? Again, when we're going through and calculating these test statistics, this says under these conditions, this test statistic will follow this distribution. And if I start to violate those, I still have a test statistic that follows the distribution. I just don't know what the distribution is of that test statistic. And so I start applying, sort of this is the probability of obtaining this value under these types of things, but all that starts to fall apart, right? I've got, if I say violate my homogeneity of variance assumption of a t-test, remember that if this is my t-test with degrees of freedom 20, right? I got 10 in one group, 10 in the other group, or excuse me, 21 in one group, 21 in the other group. And so my test statistic, the sampling distribution, my test statistic is going to follow this distribution, and I can say, if here's my critical value and this is where I found my thing, then sort of, yep, then this is it would, assuming that the null hypothesis is true, it would be unlikely to obtain a test statistic if these two samples were, or these two populations had equal means, right? So I'm going to say it's low probability, so I'm going to reject the null hypothesis, it claims statistical significance, so on and so forth, right? But as soon as I violate all my assumptions, then my test statistic, I don't know what distribution my test statistic has. It might be this, right? Or it could look something like that, right? I don't know, with wacky assumptions or huge violations of assumptions, maybe this is what it looks like, right? So I've calculated this score and identified it as that is statistically significant, but maybe it is, maybe it isn't, sort of p-value is all wrong. I start to lose confidence in the precision of my estimates. And so with our screening, always want to go through and if we say, these are the rules of the game. If I'm going to do these analyses, this is what these analyses are assuming the data are doing. And if the data aren't doing that, I want to know so I can start to qualify my interpretations, make appropriate adjustments for corrected statistics, things along those lines. So very important. Also, just as a good research scientist, this is starting to give you, if you go through and you do this, you're going to have an intensive understanding of what your data are looking like, right? you walk into any defense meeting or any sort of meeting with a colleague and be like, this is what they're doing, this is what it looks like, well, what about this? Like, nope, that's not happening. I've already gone through and taken a look. You'll know distributions, you'll have a sense of min-max values, you'll have a sense of how things are correlated with one another. It's just a really, really nice way to go through and sort of get immersed in your data and really know what's going on. Also letting you to sort of go through and take a look at, this is what I was trying to do with this study, was it effective? Right, think about this in terms of an internal consistency type of thing. In the example of question 2 that you have in this problem set, right? I've gone through and I've said, okay, I'm going to go do X, Y, and Z, and sort of the purpose of showing these different films is to get different stuff, right? Well, maybe that happened, but maybe it doesn't, right? Are our manipulations always successful? Nope, not always, right? And so it's a good way to go through and take a look and say, based on the assumptions of my design, based on what I did, this is what I should be seeing in these data. Did I see that? And if I didn't, then even before I'm running through my analyses, should sort of have a good sense that maybe something went sideways on me on this. Okay. Also, thinking about continued research questions and sort of designs, things along those lines. I might find that in this condition, everybody kind of did what they were supposed to. In this condition, everybody was all over the map, right? And so I may have a violation of my analyses, but maybe that's the least of my concerns. Maybe what I'm really interested in is why was everybody over the map in this condition versus not? What's going on with this manipulation that created, it looks like chaos in terms of scores. Maybe there's something important in there that I need to be thinking about. Hey, I ran these analyses and this is, Baumeister did it, so it'll be perfect when I do it, right? And I find that it doesn't work, and it doesn't work, and it doesn't work. Is there something wrong with this paradigm? Is this not doing what I'm supposed to, what I think it's going to be doing? These are things you can start to pick up in your screening. So in total, this is going to take far more time than your actual analyses. You'll spend twice as much time, 2 times, 3 times as much time with screening as your actual analyses? Probably, right? Just, and the analyses piece gets easier, so don't let that scare you, but it just ends up being more time that you spend going through, working with your data, seeing what these variables look like, understanding sort of what's happening there. And so again, this is gonna, by the time you finish up, it'll give you a better sense for how to interpret these data, what this means within the context of your research question, and then be able to, when a reviewer 2 says, you need to do this, you'd be like, no, that doesn't make any sense given X, Y, and Z. You'll be able to go through and talk about it. Also make sure that you don't, your entire study isn't being driven by, all your results are being driven by 1 or 2 points in the data, because that's not good news in terms of replication and things like that. So we're going to go through, this is all going to look super familiar. Plausibility, missing values, distributional assumptions, linearity assumptions are kind of new. We'll get into some of that, and some stuff with the variance assumptions are a little bit different with the multivariate screening, and then collinearities, singularities, stuff that we'll cover with this. But again, a lot of this is going to be repeat because we've talked about it before last semester. So accuracy, plausibility. Again, looking at expected range. Our data falling within sort of the reasonable bounds of whatever scale we're using. Are all our variables coded appropriately? I went through the full semester where I sort of had a semester's worth of data where previously women were 0, men were 1, and then I reverse coded it. And then at one point I was screening my data, I'm like, we had a bunch of men in the fall of 2015. What was going on with, oh, whoops, I just reverse coded those and sort of, it's an important thing to know, particularly if you're going to include gender as a variable, or biological sex as a variable in your model, right? So wanting to go through, make sure that your variables are coded appropriately. I know from our work that we get far more women than we get men, and then all of a sudden I'm seeing that I've got way more men than I have women. That's not plausible. Let me go back through, whoops, here's the mistake, go through and fix it, okay? Labels applied correctly. Maybe I did sort of women are 0, men are 1, it's always been the way it is, but so I got the labels backwards on something, right? Or if I see that I have a disproportionate number of minority participants in my study, that should trigger me because I'm at the University of Wyoming. That doesn't happen, right? Making sure things have been labeled correctly. Particularly if you're going to share data. One of my biggest headaches is like, oh, here's data, can you help us out with this? And it's just a bunch of stuff. I'm like, I don't know what any of this is. I don't know what it means. None of this makes sense. Always go through, label your data, set up your data set if you're going to share it with anybody, your advisors, colleagues, things like that, so that it's very crystal clear what variables mean, how they're coded, things along those lines. And then, do I have the expected number of cases? This is one of my peeves again. If I'm looking through reviewing a paper and then all of a sudden degrees of freedom are jumping around in terms of different analyses, that suggests to me that we're not using the same people to test all these different tests, which to me is problematic because it starts to decrease the generalizability, right? So making sure I should have, 75 people in these analyses. If I start coming up with less than that, I need to go through and make sure I haven't missed missing values, okay? So in SPSS, again, looking at frequencies, descriptive statistics, to go through and make sure all this stuff makes sense within the context of the data that I'm using. Missingness. Any questions about this? We've been doing this for a semester and a half now. Questions here? Okay, cool. Missingness. This starts to get tricky, okay? We've talked about, to this point, so that identifying missing cases, and so this is the number of people, and so then we go through, and what I've had you do is just get rid of those cases that are missing values and they're relevant to the analyses, because then during your screening you can't have accidentally I get 64 cases looking at this variable and 63 at this variable because this one case won't be included in the final analyses, but I left it in and it has a value and now it's being included in the screening and stuff like that. Just go through and have you reduce it down to just the cases that are going to be included in your final analyses. But one of the things we needed to do before we sort of cut that down is start thinking about if I do have missing data, what's the mechanism of that missingness? What's the pattern? Why are these data missing? Okay, and in general, the mechanism of missingness is much more important than the amount of missingness you have. Now, if you have missing values in like 3/4 of your data, that's obviously problematic, right? But for the most part, what we want to see is why are these data missing? This is why when I'm going through and having you do your screening, I don't just want you to say, oh, there are six cases with missing value on the outcome, right? I want you to tell me what the case numbers were, and if it's group-based analyses, was it condition 1, condition 2, what condition were these people in? Because then that starts to become important in thinking about the mechanism, right? Do I have a case where, and this happened when I was at Buffalo for my third year project, we were going through running physiological stuff for a film paradigm, and my RA came back and she was very nervous. She's like, I keep losing data on our African American participants, right? She's worried like physio equipment were racist or something. But what we're using for heart rate was a pulse oximeter. Anybody know what that is? Yeah. What is it?
It's like this little thing that goes in your fingers and measure oxygen flow.
Yeah. So we can go through and measure heart rate, but what it does is it sends like an LED light through your finger, or I think it was a finger we had, might have been the earlobe. Anyway, it kept, for African American participants, kept dropping it, right? But when you go through and take a look at sort of methodology on this, sort of darker pigmentation makes it, and so you're losing stuff, right? But if I've lost heart rate for, disproportionately in my minority candidates, that's systematic missingness that starts to become important and recognized, right? And so wanting to go through and take a look when we've got missing data, where is it coming from, and understand why that's happening. Now, if we've got a version of random missingness, we often refer to this as ignorable missingness, right? If we have some form of, if it's truly random, or I have a variable in my model that accounts for that missingness, we would identify this as ignorable, and so we're less worried that this is going to unnecessarily bias our results. But if I have non-random missingness, this is the types of missingness that's going to start to go through impact, inference, generalizability, things along these lines. Okay? So I gave you a handout from kind of written up from one of the readings. It's on your on the syllabus, going through taking a look at somewhere. Mechanisms of missingness. I think this is a. Yeah, this is based on this. The Schaefer and Graham paper. Go through, read this, read that paper. This starts to become increasingly important when we start thinking about things like multi-level models and SEMs and things like that. When we're using estimators that will account for missingness in the data, right? One of the assumptions of, say, maximum likelihood, everybody gets excited about maximum likelihood because it accounts for missing data. Well, it does, as long as your data are missing at random or missing completely at random. If you have systematic missingness, it's just going to bias all your results still, right? So important to start thinking about patterns of missingness and mechanisms. If we're talking about something that's missing, data that are missing completely random, defined as probability of presence or absence of a value of y independent of all other variables, including y. Okay. Within this Little and Rubin's sort of mechanism or category here, we're saying that if y, so whether or not y is present or absent, my outcome variable is present or absent in my data, is independent of all of the variables. So whether y is present or absent has nothing to do with any of the other variables in my model, right? It also has no relevance to the actual value of y, right? So higher y's aren't missing, lower y's aren't missing. This is what we would say missing completely at random is consistent with what we would typically say if we're talking about random missingness. Whether or not I have a value for y or not is completely independent of anything else in my model, observed or unobserved. It's just a completely random thing going on. Okay. This one's easy to wrap your head around, but questions on this? Okay. Where it starts to get difficult when we start talking about missing at random. Okay. If we have data that are missing at random, probability of the presence or absence of a given y value is dependent on observed values of x or some combination of x, but unrelated to the actual value of y after we control for x. Okay. What this is saying is that whether or not I have y or don't have y isn't random, right? There's some reason why I'm missing y, right? But the reason that I'm missing y is related to one of my predictors, okay? So if I'm, let's see that sheet. So if we look on, so here in the example provided here, it gives sort of examples of different missingness. For the missing at random example here, we see that readings on our outcome are those collected from patients with January heart rate, blood pressure ratings less than 140. So if I have blood pressure ratings less than 140, I don't have, it's sort of before those values are missing from the subsequent one, right? So the presence or absence of whether or not I have a heart rate value at the target one that I want to look at is dependent on the previous one, right? If the previous blood pressure value was below 140, then we didn't worry about it, we didn't assess it again. But if it was higher than 140, then we've got a value here, right? So our value on our outcome isn't random. It's dependent on on a previous assessment. But if we go through and we have that other variable in the model and we've accounted for it, and once we account for that variable, then whether or not we have missing on our subsequent outcome is sort of happens at random after controlling for that, then we would say that these data are missing at random. Okay. So again, in this example, I'm going in sort of looking at people's blood pressure ratings is sort of across. But if we go through really closely, we see we have missing values predominantly because we only took values at this time point if people had high blood pressure at this time point. But if we have all the people's values for blood pressure at this time point, as long as we have that in whatever predictive model we want to take a look at, and after we account for that, the only other people who are missing values just because, I don't know, equipment went down on that day or something like that that have nothing to do, they're just kind of happening at random, then we've got our data that are missing at random. So essentially, this is the big thing to be thinking about this. With missing at random, I have non-random missingness, right? Missing, I have the data in my, on some variable are missing for a reason, but we know why it's missing. And we have a variable that accounts for that missingness. And if that's the case, then we still have ignorable missingness where our mechanism is missing at random. Kind of see the difference between missing completely random and missing random? MCAR and MAR. All right. If you have missing not at random, this is a situation where we have probability presence or absence of a given value of y is dependent on the actual value of y and also maybe on values of other x's as well, right? So if my blood pressure is missing because my equipment is old and it drops out at systematically higher low blood pressure ratings, and so then for just sort of random, or is it then for a number of cases in my set, I'm missing blood pressure, but the missingness is because of something systematic in my equipment. So if I either have very high blood pressure, it's missing, or if I have very low blood pressure, it's missing. And that data is missing not at random, right? Because the mechanism of missing this is a function of the actual value of y, right? If we actually had those variables, we could see, oh, it looks like all our high variable values are missing, all the low values are missing. Well, we don't have that because those values are missing, and so then we've got a problem. Or maybe whether or not I have a value for my outcome variable is functionally related to some other variable in my model. Let's say that I'm missing questionnaire scores in MTurk because if I had someone who's just really angry and they quit, right? And so all my angry people, I'm missing scores from all my angry people, right? Now if I have a PANIS at the front end of it, and I can say, all right, well, I measure your mood at the front end. I see that you really negative affect. I see the people with a really negative affect are then sort of missing the scores on the outcome. What type of missingness do I have here? What do you think?
So the people that high.
Well, so I've got, but I've got those PANIS scores in the model. What do you think, Kate?
Is it at random?
Yeah, it's missing at random, right? Because I've got those PANIS scores, right? And yes, my outcome, my y variables aren't missing at random. It's the people who were pissed when they came in that didn't complete the survey, and so I'm missing survey scores for those people, but I've got their mood up front. And if mood is what accounts for the missingness on that back end, then I'm missing at random. I've got that, I can go through and account for why that data is missing. But if I didn't collect mood at the front end, right, and I don't have a measure that calculates mood, then what I've got, missing not at random, right? My values are missing because of some systematic other variable that's not included in my model that I don't have access to, right? I can suspect, right? Like, I think what happened is that people just got tired of doing this, got angry, and then stopped. But if I don't have a measure of that, then I'm stuck down here because I can't account for that in my model. So I'm only getting outcome, and I'm only analyzing data based on people who are happy. And then if I'm using like a maximum likelihood estimator, it's doing the best with the data that it can, but basically it's estimating missing values, and so if those people were happy, those are the only data that we have. That's actually not the case. They're mad, that's why they're missing. And so what we've done is we've biased our estimates because of we've got systematic missingness in our model that's not accounted for by something else in there. Okay. So these are the types of things that start to become important when we're thinking about what's my missingness look like? Why are these data missing? And then sort of thinking carefully about this and not just assuming like, oh, this is all at random, right? Particularly in clinical types of things, right? So all of a sudden, you know, my people who are most severe are the people who I'm not getting data from. That starts to become problematic, right? Because one, the people I'm most interested in aren't filling the stuff out, and then two, I'm making estimates based on sort of people who are low end and not the people who are on the high end are being represented, and it starts to become problematic from this standpoint. Okay, so again, Tabachik and Bedell, chapter 4, Switzer and Roth, these missing data. So definitely go through and take a look at this. This is it's kind of hard to wrap your head around because the probability of X versus this and that, the other thing, but it's an important thing to start to be thinking about when we're thinking about generalization biases and things along those lines. Okay. This is a huge, huge issue for the soapbox I'll get on for clinical stuff, right? People want to go through and they'll do, okay, here's my RCT for sort of this sort of treatment, and I'm following people, right? And so what we did is we used an HLM or something like that to address missing this data for people who sort of discontinued treatment, right? Is that an appropriate thing to do from a basic statistical standpoint? Do people drop out of treatment randomly? Do we know why people drop out of treatment? Nope. So that tells me we got a goddamn problem, because we're assuming that, oh yeah, it is accounting for the missingness, right? So this estimator will just sort of go through and provide the best estimates based on the available data, right? But the reason we have missing data isn't random, it's because of something. Something made these people drop out. You don't have just random people dropping out just for no reason at all. There's a reason, but in our field, we don't know why people drop out. That'd be awesome if we did. If we could predict who's going to drop out of treatment, that would be really cool, but we don't. But we still run these analyses as if these data are missing at random or missing completely at random, and then pretend that it's fine, and it's not. And so who knows, right? Basically what this model is doing is it's estimating sort of subsequent assessment points for someone if they would have stayed in, but it's making that assumption based on the people who did stay in. That's not who we're missing data on, we're missing the people who didn't stay in, and so all of a sudden it starts to, who knows what it's doing to our estimates of the extent to which treatments work and things along those lines. So with the advent of sort of longitudinal HLMs and things along those lines is sort of very exciting. It's like, oh, we've got this sort of estimator who will go through and address a major problem with longitudinal research is we lose people, but unless we know why we're losing people, that's not an appropriate technique to use, because the assumption of the estimator is that those data are missing at random or missing completely at random. If we knew why, right, then we can go through and sort of, then they're missing at random. But if we don't, then we're down here and then we've got bias problems. Questions about this? My small rant that goes into review papers a lot, but okay, cool. All right, distributional assumptions. Univariate normality, you got univariate normality. You guys are experts at univariate normality. Multivariate normality, this gets a little bit different. We touched on this in one of our earlier lectures. If I have data that are univariate normal, I'm saying that each variable and all possible linear combination of variables have a normal distribution, okay? And so we talked about bivariate normality, extension of normal distribution. We're saying that, again, if we take a look at sort of this three-dimensional plot, right? Again, if I have, say, my x variable, throw up your thumb, x variable, y variable, right? So we've got this Cartesian plane out here. Then what we do is throw up a z-axis here in three-dimensional space, and this is our frequency, right? So we've got frequency here, frequency on y, and if our data are completely uncorrelated, what does that three-dimensional distribution look like? Kind of like an anthill, right? It sort of just goes out in all directions. What we've got here is something where we do see a linear relation between x and y. We've got something that kind of looks like a kind of a thin stegosaurus signal thing. All right, but the thing is, if we go through and take this three-dimensional plane, cross-section it across any value of y, cross-section it across any value of x, if we look at that cross-section, Amelia, what's the distribution of that cross-section going to look like? Yeah, if we sort of take it here, what's this going to look like in terms of the cross-section?
I understand.
Because I probably phrased it inappropriately. So if I take this plane right here and I cut it, right? I slice it and then look at it from the front. What's the shape? Exactly. It's just normal, right? It's a nice normal curve any way we take a look at it, right? And so if we slice this like this, we're going to get something that looks like that, right? Because we're looking at it at the end. If we slice it down this way, down to 0, right? So we are saying what is the distribution of x based on what is the distribution of y when x is equal to 0? This looks like it's going to be something kind of longer or something like that, right? And so for in three-dimensional space, multivariate normality says that each variable, all possible linear combinations of variables, normally distributed. Okay, we'll kind of see what we're talking about here, right? Now this is difficult to test directly. It's hard. What we have to do, we have to go about this looking at indirect, and we'll talk about how we go through and try and tease it apart and see whether or not our data meet assumptions of multivariate normality. A lot of our univariate, multivariate tests are generally assumed to be robust to this. But this is starting to become called increasingly into question. This is like anything else. What happens is when we're running things by hand and through punch cards on giant mainframe computers, we say, hey, this probably isn't great, but it looks like it's close enough given what we've got. As we go through, we start to get more increasing computer power, more sort of sophisticated means of estimating our outcomes and things like that, starting to recognize that no, some of these things actually do start to have a big impact on, or potentially a big impact on our inferences, and starting to recognize that, yeah, this is something we need to take a little bit more seriously. So, always test these assumptions. All right. In terms of thinking about multivariate normality, the way we go about approaching this is going to be a little bit different if we're talking about grouped versus ungrouped analyses. Give me an example of a grouped analysis. What do you think, Evelyn?
Like the VDI example that we did in class last week, where each program is a group.
Okay, yeah, that would be a grouped analysis, right? So ANOVAs, t-tests, things along those lines, those are going to be group-based analyses. Our ungrouped analyses, these are going to be things like our regression models, things where we're having dichotomous and continuous predictors along those lines. So for our ungrouped data, okay, we're going to assume multivariate normality if each one of our variables, as long as it's continuous, not dichotomous, right? Do we expect dichotomous variables to follow a normal distribution? No, it won't. So no need to look at skew and kurtosis for dichotomous variables because that doesn't make any sense, right? But for our continuous variables, we're going to assume in our ungrouped analysis that we've achieved multivariate normality if each variable follows a normal distribution and our bivariate relations are linear and homoscedastic. Okay, and we'll talk about what that homoscedasticity is. Basically, I'm saying that if I've got, for all of my x's and all of my x's, all my variables, that I have a linear relation, and so the variability around my points is all kind of reasonable, right? So this is a relation between x and y in which I have a linear relation and I have a homoscedastic relationship. Basically, this is a generalization of your homogeneity and variance assumptions. Okay. Now, if I have data that looks like x, y, same relation, is that homoscedastic? Nope. Why not? I mean,
It doesn't follow the linear path. So
well, it still follows a linear path.
that has that.
Right, maybe I got this guy on here. Right? What's going on? What's the difference between this and that? What do you think, Kenny?
The variance is much larger between the points at the bottom.
That's what we're looking at, right? For low values of x, my variability of y is huge, right? As I start to get, as x increases, the variability in my y starts to get quite small. We see this fan-shaped pattern where we have much more variability for x at e being low versus x equals at high levels of x. And this is where one of the things I'm excited about, sort of moving our lab over into some stata and stuff, because there are actual it'll run some regression analyses that address this, is what I see in a lot of our data, and you'll see it too because you're analyzing my data because it's the data that I have. But if we have something like, say, I get something like this, and this is some measure of functioning, something like this. That's the pattern I get in my data, right? So we're saying at low levels, so if people have little to no PTSD, let's say this is PTSD and this is anxiety sensitivity or something like that, right? At low levels, I don't get a lot of variability in my outcome because everybody's fine, right? But as we start to get with increasingly severe symptoms, by the time we get out here, right, we have wide variability. We have people who are really high in PTSD but maybe have low depression, but also lots of people who have super high depression and everywhere in between, versus down here, if you have no PTSD, you don't have a lot of variability around things. And so what ends up happening as my predictor increases, variability in my outcome starts to increase, right? And there's a lot of reasons that this can happen. We'll go through and talk about what's going on here. So this would be a relation that's linear, but it's not homoscedastic. Okay, multivariate normality, pretty complicated. If you wanted to get an exact test of it, and there are tests of multivariate normality, and whether they're good or not, there's limited by some of our other tests of normality, right? If I have a sample of 500 and I find that my test of multivariate normality is significant, right? Like, well, is that because I have wildly problematic data, or just because I have 500 people in my sample and any deviation of multivariate normality is just going to be statistically significant? That's the type of thing we run into. And so this is where our graphical methods are going to come into better play with this. But if we're working with our undergroup data, we want to see that our individual variables following a general normal distribution and that our relations are linear and homoscedastic. Okay. Questions on this? All right, for our grouped data, remember, and this is review, normality assumption refers to the sampling distribution. It means not the exact score, okay? So we don't actually care about, well, we do care about what the distribution of our outcomes are. We're just more concerned about is our sample large enough so that the distribution of sample means can be assumed to be normal. And then under what two conditions my distribution of sample means start to become normal? My sample increases, and what else? small sample sizes. What's the other thing that will tell me that my distribution of sample means will approach normality quickly? If it comes from a normal distribution, right? So if I've got, let's say, IQ, right? And I go through and I have a sample of 10, right? My sample is the distribution of sample means going to become normal very quickly at sample size equal 10. Maybe not, right? But let's say I've got right, something like that, right? That's kind of, but it's got a kind of a skew going on here, right? But if this is IQ and this is n equals 10, whatever, right? Distribution of sample means is going to be normal in there. As long as I don't have, with n equal 10, what I'm more concerned about is outliers dragging that mean around, right? But as long as whatever I'm measuring is coming from a normal distribution with the population that I'm looking at, I'm still going to be probably okay with stuff. Okay. So questions about normality assumptions. A lot of it's review, but it's a nice refresher. Okay. Refresher on distribution of sample means. Can't go over this enough. Can't have a strong enough understanding of this stuff. It's just fundamental to everything that we do in inferential statistics. Remember that our distribution of sample means is the distribution of means obtained from all possible random samples of a particular size that could be selected from the population, right? Sort of individual values in this graph here, these are means, right? This is how often we get this as a mean, how often we get this as a mean, this and this and this. So let's say we took random samples of adult height and of sample size 100 and plotted those out. This might be what we would get in terms of that, right? We know that through the central limit theorem, for any population with mean mu, standard deviation theta, distribution of sample means of size n will have a mean equal to mu, standard deviation of the standard population standard deviation over the square root of n, and will approach normality as n approaches infinity. So what we're saying is the mean of our sampling distribution is the mean of the population, right? The mean of the sampling distribution, or the expected mean here, is going to be equal to the population mean. This is nice because we can't ever actually we can't physically test the population mean in almost all cases because we don't have access to all the people in the universe, right? But what will happen is the standard deviation of this distribution starts to change based on my sample size and the standard deviation of the population. Okay. So if I have, sample size equal 20, would that graph look different than the graph that we have here?
It's gonna have more variability.
It's going to have more variability. Is the mean going to be different?
Maybe. But decreases to 20?
Was it? Yep.
No.
No, right? Because what I'm going to do is from a theoretical standpoint, I'm still taking all possible samples of 20 that could be drawn with replacement from people in the U.S., right? So the distribution, the mean of my distribution of sample means is still going to be equal to the mean of this distribution of sample means. It's just the variability of that's going to be much wider, okay? And so again, distribution of sample means starts to approach a normal curve very quickly if the population from which the samples are drawn is normal, so my outcomes, if I'm looking at IQ, height, things along those lines, then even if I have small samples, distribution of sample means is going to approach normality very quickly. But sometimes we're measuring things that aren't normally distributed in the population, right? Kate's looking at heroin use, let's say, right? That's not something that has a normal distribution in the population, hopefully, right? It's going to be very, very skewed. But still, if our samples are, and it's not even that huge, right? 30-ish, that's our rule of thumb. But what we start to see is as long as we have a good collection of people, even if my sort of outcome is skewed like this, on average, we're going to get low scores, low scores, low scores, and then I'm going to get a high score and a low score, right? In terms of my sampling distribution, it's still going to end up turning out to be normal. Okay. So again, important concept I went through and put together and gave you guys a link to kind of a screencast demonstration of what this looks like and how this kind of works. Some other stuff, if you're sort of want a refresher, that'd be a nice thing to go back through and take a look, just so you have a handle on this sample distribution stuff. Okay. So questions on distribution of sample means, central limit theorem, mean of the sample means equals population mean. Comfortable with this? Okay. Again, central tendency, the mean of the distribution of sample means, the average of all possible sample means of a given sample size is going to be equal to the actual population mean, right? So if you think about this in terms of, say, political polling, right? There's a hypothetical value of an approval rating for a politician out there in the universe, right? We can't directly observe it, but there's some theoretical value out there of the level at which, if we were to pull everybody in the U.S. sort of approval rating of this person, and this is what it would be, right? Now, are we going to get that same? Is that the value that we're going to get for every poll of 1,000 people? No, right? Some of it's going to be high, some of it's going to be low. Some of them we're just going to get random samples that are very, very high. Some of them we're going to get random samples that are very, very low. But on the average, if we took the average of all sort of approval levels of all possible samples of a certain size, what we would end up was with a distribution, and the mean of that distribution, the expected value of the mean is going to be equal to the population mean. Okay, this is a foundational principle that all of our inferential statistics are based on. Okay? So here, if we say this is random samples of adult height, of sample size 100, if I were to, in the U.S., go through and take all possible samples of 100 that I could, plot out those means in a frequency distribution, the mean of that frequency distribution would be equal to the actual population value that we're interested in. And then the variability, right? Evelina says if, as our sample size goes down, our variability of our distribution of sample means increases, which is exactly correct. And we refer to the variability of the distribution of sample means as our standard error, right? This is super important. Think about your standard error as the standard deviation of the distribution of sample means. A lot of different ways you can think about it. These are all good ways and sort of ways that sort of actually put some meaning into this. You can think about your standard error as an index of how much a difference is expected from one sample to the next, right? So I've calculated my t-test, right? I've calculated my mean value, right? And then I have a standard error for that mean value. That standard error is telling me how much of a difference on average I should expect that point estimate to jump around if I were to resample and resample and resample and resample from the same population to the same sample size, right? And so you can look directly at your standard error and get a sense for, is this good or bad, right? We often don't think about it that way, but you can literally look at, if I were to do this again, on average, how far would I expect this value or estimates to jump around from this value, right? You can also think about your standard error as how well an individual sample mean estimates the actual population mean. Okay? So here's my estimate, looking at my standard error. How far on average do I expect this mean to fall from the actual population mean? My standard error is really big. It tells me my estimate probably isn't that great. If it's very small, I know that I've probably got a pretty good handle on sort of what something that's close to the population value, probably, right? That doesn't mean I don't have a random sample that just happens to be out here or happens to be out here. Nick, do I know if my sample's out here or out here? No, I don't know, right? The best I've got is just, well, now, if I'm looking at height and I get an average height of 6'5", I probably have an idea that I got a weird sample. But for a lot of the stuff that we're assessing, we don't know, right? So this is what makes it difficult. But what we can do is we can take a look at that standard error, and assuming that we didn't get a weird, wacky sample, we know, so we can get a sense for about how good our estimate is. And Kate, what happens? How do we improve our estimates? How do we reduce our standard error?
Increasing
sample size, right? So if I'm looking at mean height and I have sample size of 100, I'm going to have I worked this out based on stuff I found on Google. This was figuring my standard error should be about a little over a half an inch. That's pretty precise, right? That's if I have a truly random sample, right, of people in the U.S., of adults in the U.S., that's pretty good, right? But if I have a sample of 10, what's going to happen to my standard error? It's going to go through the roof, right? And so say, all right, this is my point estimate. I should just recognize it's not a very good point estimate. And if I were to sort of saying how close, how well does this truly estimate the population mean? Probably not great, right? So on average, it's going to jump around by 3 inches, or it could be more, who knows, but on average, this is kind of what we've got. You can also think about your standard errors, the expected difference between the sample mean, the population mean, right? So how much distance going on there. So basically taking all of the same interpretations that we have of standard deviation and just applying that to your standard error, because your standard error is just the standard deviation of your sampling distribution, and thinking about how much would I expect. So this is my point estimate, this is my best guess, how much would I expect this to jump around with repeated samples using the same methodology, the same sample size, from the same population. Right? And this starts to take on, particularly in areas where people are becoming more concerned with replication issues and things along those lines. This starts to become important in sort of understanding why it was inevitable that this was going to be an issue, and questions of why people are shocked that this is going on, because everything that we know about statistics say, yeah, it's probably going to happen. Okay? So, bigger samples, the better. That's the best way to sort of go through and do this, and then sort of good methods and things along those lines. All right. Questions on sampling distribution, standard error, expected values, and mean, anything like that? Okay. We'll run through skew, univariate normality, skew, and kurtosis. Skew is your third population moment. It's a metric of symmetry, right? Positive skew have tails extending towards a higher value. Negative skew, tails extending out towards the other side. This is a nice thing and a helpful thing to keep in mind. If I have a skew distribution, my mean drug all the way out towards the tail. My mean is going to be the farthest place out. My mode is going to be where the hump is. That's going to be on the other side. My median, and so for a skew distribution, if I've got significant skew, what's my best measure of central tendency?
Median.
My median, right? Because it's really going to give me the middle value. That's what we should be looking for. Negative skew, same thing. Negative skew says values are drug out towards the negative value, or the lower value. Again, mean, drug out towards the tail, mode there in the hump, median right there in the center. Okay. So if I have a distribution that's notably skewed, means no longer a good measure of central tendency. And so wanting to make sure that sort of we're recognizing this if it happens. Now again, when we're assessing skew in psychological data, I've mentioned this before, it's worth mentioning again. Let's say I have values that are really kind of sort of drug out there. What's the first thing I should be thinking about trying to decide whether or not that skew is important or could impact my data? What are some things I want to consider?
If all your values are within the range that you're expecting.
If it's in range, sort of making sure that I don't have anything that's sort of like not a reasonable value or something that falls outside the scale. What else about the range should I be thinking of in terms of trying to gauge the impact of having sort of values out there?
Outliers?
Outliers, yeah. What about something even more fundamental? The scaling, right? A lot of the measures that we use, they don't go to infinity, right? There's only so far you can go, right? If I've given someone a 0 to 8 scale of valence and arousal or something like that, right? At most, they can cap out at 8, right? If the average is 2, and I've got a couple people at 8, probably not gonna be that big of a deal, right? Versus things if we're in different fields and looking at things like income, then that can start to go through and drag stuff way out of bounds, right? I'm looking at income in undergraduates, right? So I'm measuring income in youths, undergraduate income, but then I've got a non-traditional student who's an engineer who's just taking extra stuff because they want to, right? And they're making 6 figures or something like that. All of a sudden, yikes, I need to make sure that I identify that because that's going to drag that way out of bounds, right? So we're actually in a pretty good position, I guess. So our measures are imprecise and rife with error, but there's generally an upper bound like for how far up you can get, right? So that's one of the things we want to be thinking about. What's the other thing that starts to help us maybe be less concerned about having values that are at least sort of higher? We're worried about stuff dragging our mean around.
Sample size.
Sample size, right? If I've got someone with a crazy high value, but I got a sample of 70, 80, 100, probably not worried about it, right? Is that within the context of the types of things we measure? Right now, if I've got Jeff Bezos in my undergrad income sample, then that's a problem, right? But for the types of things we're typically measuring, if we've got a reasonably sized sample, the impact of one huge value is probably not going to be all that much, right? So wanting to think about these things in terms of, you know, making an informed decision on whether or not this is a problematic value or not, sort of within the context of these data, as opposed to saying, this Z was over 3, and so we're going to get rid of it, right? Because it's an outlier. Oftentimes, you'll end up throwing out the people of most interest if you start doing that. All right, kurtosis, our fourth population moment. This is describing the shoulders and the peak of our distribution. Our positive kurtosis peaked, sort of peaked top, and heavier, thicker tails. What's our classic example of a leptokurtic distribution? Remember? Distribution we use all the time.
Is it T?
It's RT, particularly at low degrees of freedom. It's got a sort of a narrow top, flatter tails. As the degrees of freedom increase, RT distribution becomes asymptotically identical to a normal distribution, right? But particularly at low degrees of freedom, it's kind of a narrow peaked top, flatter tails, which is why, you know, what am I, for alpha equal 0.05, what's my critical value for Z? 1.96, right? But if I'm using a T distribution with 20 degrees of freedom with 1.96 giving me a significant result, no, it's not, because it sets those markers out. You got thicker tails, there's more stuff going on there. Right? Our negative kurtosis is a distribution flat and centered, heavy shoulders, so you don't got those tails, it's kind of sort of domed, right? Square distribution is kind of a perfect, like it's a perfectly negative distribution, right? So I've got 20 values, or I've got 20 observations, I've got 4 values, 5 in each of those 4 values, so I've got a square distribution. That's going to be something that would be negatively kurtotic, right? So we've got big shoulders, not a lot of tails. The thing to remember is that kurtotic distributions underestimate the population variance. Okay? Kurtosis, whether it's positive, whether it's negative, kurtosis always, the concern is underestimation of population variance. Here, with positive kurtosis, we got those tails that are jumping out, right? But we're missing all the middle stuff, right? So the tails don't make up for the stuff that we're missing in the shoulders. For negative kurtosis, we've got all the stuff here in the middle, but we're missing the stuff in the tails. In both of these cases, we're worried about underestimation of the variance with a kurtotic distribution. Okay. And so again, what this can do in smaller samples can start to contribute to parameter biases, standard errors, and things like that, right? If I've underestimated my population variance, what's that going to do to my standard error? What do you think, John? But underestimate. Questions on anything up to this point? So this is all pretty straightforward, things that we've done before, but it's nice to go through, get a review on this. Any questions on missingness, distributions, things along those lines? Feeling okay? All right. One of the things we want to think about, and again, this is a review on our group-based analyses. We're talking about t-tests, ANOVAs, repeated measures, designs, things like that. Typically think about these as being robust violations of normality, given relatively large samples. Even pretty serious violations of normality tend to be negligible as long as we have cell sizes that are 25, 30-ish, right? And so this Bono article that we read last year is kind of talking about some of this stuff. But things that you should be identifying as problematic as you're running through screenings, situations where our tests aren't robust, if distribution across groups have a different shape and have different variants. Remember that if we start doubling down on violations, this is where things start to become problematic. So I've got cell A has a positive skew, cell B has a negative skew, and they have wildly different variances. That's problematic, right? If we have different sample sizes and different variances, this is also an important thing to think about. So just saying, hey, this is a problem is part of it, but you're in a much better position if you can say this is specifically what the likely effect is going to be on sort of my outcome, right? So if I have large sample with larger variance, my overall estimate of variability is going to be too big, right? And my overall estimate of variability is too big. What does that do to my standard error, Layla? If my overall estimate of variability, so is my aggregate variability, estimate of variability is too big, what does that do to my standard error? It does what? It increases it. That's what I thought you said, right? Because again, remember that my standard error is my variability divided by the square root of my variance over my sample size. And if my aggregate estimate is too big, that's going to make my standard error too big. And then, Kate, what does that do to my test statistic?
Makes it too big, or too small.
Makes it too small, right? And so I have too conservative a test. But if my larger sample has a smaller variance, right? My biggest sample has really itty-bitty tiny variance, then my aggregate measure is going to be too small. It's going to make my standard error too small. It's going to inflate all my test statistics, and then I'm going to be claiming things are reliable and not, right? And so wanting to think about actual consequences. Also, if I have small sample sizes and violations of normality, this is a problem, right? I have cell sizes of 8, 10, 15, and ugly, not normal data. That's a problem. So wanting to make sure that you're noting not just, oh yeah, this is a problem, but starting to think about like what's the potential impact here. Okay. All right. Outliers. Univariate outlier, we've talked about that. Univariate outlier is just an extreme value. And again, I like to use it. I prefer extreme values more than outliers, right? Because outliers is sort of it's hard to say what is an outlier and what's not, what sort of my impact is and things like that. But again, we're looking for extreme values within a given variable for univariate outlier. My multivariate outlier, this is some sort of atypical configuration of scores. Here I've got a number of different variables coming together in a strange configuration that doesn't make a lot of sense given the rest of the data, okay? So let's say that I'm interested in looking at some sort of outcome where I'm looking at age, income, and sort of geographical region, right? Sort of where people are living, right? So if I'm looking at age of the US population, 10 years, that's reasonable, right? We have plenty of people who are 10 years old. That's not a weird value, right? People making $130,000, probably going to be on the high end, but it's still going to be within the context of things. We have people residing in the rural South. We've got a good sample, right? So we've got that, right? We've got a 10-year-old with $130,000 income living in the rural South. That's a weird configuration, right? All of a sudden, we've got 3 variables that fall within the reasonable distribution in and of themselves are fine. When we put them all together, we got a weird thing going on there, right? Something that's not going to be representative of our sample is going to start causing some problems. And so this is what we want to do to go through and start looking for, do we have combinations of variables that are sort of strange and odd? I'm glad you guys laughed. I didn't know. They put this together a while back. I didn't know if sort of Johnny Boo stuff is still
It's been
ridiculous.
Halloween costume like 3 years in a row.
Okay, nice, nice. Right? So people understand sort of what conceptually is going on with the multivariate outlier? Okay, so we've got a weird combination of scores that doesn't make sense. So things that could be going on, we could have incorrect data entry, right? It could just be an error where someone added a 0 onto, or a couple zeros onto income, or something along those lines. This is what I do a lot in SPSS. I fail to remember to tell SPSS that 999 means missing data. Hopefully you catch that earlier on when you look at plausibility, things along those lines. Then we've got the possibility that cases in a member of the intended population of study. Okay, this could be a situation where, again, if I'm interested in looking at the income of university undergraduates, and I catch someone who's just a non-traditional student who's just taking classes just to take classes, right? I might say, yikes, this is not someone who is actually among the population I'm interested in. I'm going to go through and kick that person out, right? Or what we see is our case is an intended member of the intended population, but my population variability underestimated by the sample. Right? So let's say that I'm interested in, again, we talked about this last time, right? I've got, I'm interested in height of university students or something like that, right? But I only have a small sample. I get a sample size of 20, right? And so I'm going to get most people here, 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 and then I get a basketball player, right, who's, say, 6'10" or something like that, or 7 foot or something, right? But I've only got 20, right? This person is a population. Like they're part of the population. I'm interested in them. They're a university student, right? But my sample that I've collected is small, and so it's only getting this. I'm also missing people who are quite small down at the other end. What ends up happening is I just have a small sample, and this is part of the normal population. It's probably someone who's still going to be several standard deviations taller than the mean, but this big gap here is just because I've got a small sample. I didn't have enough trials to go through and capture people who start to fill that out. So another thing that can happen with our outliers. In terms of consequences, potential for undue influence on our estimated coefficients, particularly if we've got a situation like that, that can start dragging that mean far out there, particularly if it's quite high up. And so we have to go through. And so even if it is a member of the intended population, thinking about, is there something we need to do with this person in order to try and sort of reduce the impact? Because we could have quite a bit of bias here. What this is going to do is probably drag that way out there, and now all of a sudden my estimated average height of university students is way too big because I've got one person dragging it way out there, right? We can go through and start to have inflation of both type 1 and type 2 errors, right? The likelihood of me claiming something's real when it's not goes up. The likelihood of me failing to identify something as real when it is goes up. You can start to have problems. And then we've got problems with generalizability, right? We've got a weird solution because we've got a weird case in there. And so now all of a sudden I have a model that doesn't actually map well on or fit to other types of things, okay? For univariate outliers, important to remember, we can have outliers in terms of our dichotomous variables. If we have dichotomous variables, 0, 1 variables, but we have massively uneven splits, say 9 to 1, right? Or anything even close to that sort of region, that's going to be problematic, okay? This is, starts to become a problem with certain types of categorical things. We go through and measure, you know, different demographic characteristics, things like that. So if we have low presence of characteristics of the population, we can capture them. Have to start thinking about how we want to deal with that within our analyses. what ends up happening is those cases on the smaller end of the low number category start to place undue influence on our overall model results. They're exercising much more impact on, so the average person in the small group is having a much bigger impact on our total model than the average person in the big group, and that can start to become problematic. If I have extreme splits, right, I'm looking at, let's say I'm trying to look at men and women, right, and I've got 90 women and 8 men, right? What that can start to do is actually attenuate the nature or the magnitude of the relation between sex and whatever it is I'm looking at, right? So we get correlations between our categorical variable and our continuous variables that are lower than they probably should be. And so unless these types of categorical variables or dichotomous variables are essential to the analyses, thinking about going through and just getting rid of them. Okay. If it's crucial, then we are kind of left with sort of the best of bad options. But if this is just something I kind of wanted to look at, and it's not a central focus of the study, think about doing something else with it. Now, sometimes it ends up being, because we can't, unless we code it specially, can we have categorical data in, like, say, our regression models, like nominal data, nominal variables in our regression models? No, right? So we have to figure out how to code these in some way. We got to figure out what to do with them. We've got hugely uneven splits. You know, maybe we can collapse groups or something like that to kind of make it more palatable. But problems here in terms of how do we go through it and address this. For our continuous variables, people kind of see what we're talking about. So this is important, right? This is why we go through and make sure you take a look at splits. When we're talking about our t-tests, right, we're sort of looking at unbalanced design, unbalanced groups. When we're doing ungrouped analyses with like regression, still interested in, for our categorical variables, our dichotomous indicators, sort of what the breakdown is, what's the split. And if it's really huge, right, I really wanted to look at this group, but I only got 3 members of that group versus the other 50 people in my sample, maybe that's not a variable I can actually look at because I don't have the ability to do it. And if I threw it in my analysis, it's going to throw everything way off. Okay. Outliers on our continuous variables, those you use our z-scores, right? 3.29 or 3.3 is z less than 0.001. But again, this is where you're going to substitute with graphical methods to go through and start to say, so is this an extreme value? Yes, no, based on what criteria? You know, to what extent is this going to be a problem? Is where we're going to not just rely on z-scores. We're going to look at z-scores and sort of have some sort of criteria for is this a problem or not, but also rely on our graphical methods to identify potentially problematic cases. Okay, but the thing to remember is that particularly if we're looking at very large samples, right, we're bound to have people who are extreme values if we get a large enough sample, right? If I get a large enough sample of undergraduates and measure their height, I'm going to get someone who's super tall, who's abnormally tall, right? I'm also going to get maybe someone who's very, very small, right? If I get enough people, I'm going to get, if my sample size gets large enough, I'm going to capture the ends of that spectrum, right? And so I don't necessarily, if that happens, and it will, why am I not necessarily going to freak out about the fact that I did capture someone who was big or very, very small if I've got a large enough sample? Do you think, Nick? So if I do get extreme value, let's say I get someone who's 4 standard deviations above me in height, right? I mean, that's going to happen if I get a big enough sample. Why am I not concerned about that?
Because one part of the population, because the 2, they're not going to have that much of an effect when you have your sample.
Right, right. My sample's big enough, it's going to be able to sort of weather that sort of outlying value. And I'm expecting it, right? If I get this many people, I'm going to get people who are at the high end of the spectrum, right? I'm going to get people who are reporting extreme values because that's how they're part of the population. They're out there, and if I get enough people, I'm going to capture them. But the nice thing is as a sort of what needs to happen in order for me to get a lot of those is also helping me sort of let those one individual not being a huge impact on sort of what I'm doing, right? So again, always wanting to think about some of this stuff. What ends up happening is that what's a problem is when I have a sample of 20, I just randomly capture some who's 7 foot, and then I'm like, now what do I do with that person, right? Okay. So questions about outlying values in terms of our dichotomous indicators or continuous indicators? Yeah.
So we did a screening through the meeting for the Z-scores, and it was 3.29 value.
Yeah. I mean, and this is the thing, again, what I don't want you to do is say, oh, this was 3.28, so it's fine, I'm not gonna talk about it, right? And you might even in your screening talk about people who are identified, maybe they made, 2.90 or something like that, but it's a value that's separate from the rest of the distribution. It's kind of hanging out there on its own. If it's worth mentioning, then you just go through and say, I had one person that fell away from the larger distribution associated with the Z-score of 2.90 with an X value of sort of whatever that X value is. And I like that. That's important because the Z-score associated, let's say it's an X value of 20, right? Now, that value of 20 in this sample might get flagged as 3 standard deviations above the mean. If I have a larger sample, maybe it doesn't. Maybe in the larger sample, it's just sort of kind of a normal thing, right? So anytime we talk about having extreme values, I always like to see in the screening, like telling me like what's the actual value, right? So I get a sense for, oh wow, yeah, it is. So within an example that we'll do in class, looking at data where we're calculating like cumulative trauma history, the number of traumatic events someone's reporting, right? And so if you've got a low trauma group and someone has a value of 4, then maybe that's a big value, right? But if you're actually getting a trauma exposed group, the value of 4 different events is actually not really all that huge, right? And so reporting what, not just your Z-score, but the actual values associated with that for that case, that helps put into context where that person lies. Questions? Other questions about this? That's a good question, right? So not wanting to be beholden to, oh, if it's above this, yes, then they're below that, no, it's sort of not how. If I have very little variability, right, and everybody's sort of right on top of each other, and sort of small sample size, that could be a problematic value that we need to do something with, right? Okay. All right. Box plots. Remember, just as a review, the midline of our box plots, these are our median, right? These are our 50th percentile. This is the middle value of the distribution. Our bounds of the box, the upper and lower bounds, this is going to be our first and our third quartile, right? 75th percentile here, the 25th percentile down here. Box is covering the inner quartile range. What else do we call the inner quartile range? Your middle 50. So middle 50% of the your middle 50% of scores is going to fall between your first and your third quartile by definition, because that's just how it's constructed, right here. Your whiskers. This is either the maximum or the minimum values in your data set, or values that are 1.5 times the inner quartile range. And this actually turns out not to be true in SPSS. I don't know what SPSS is doing with this, and I haven't been able to figure it out. But it's what it should be doing, so just interpret it as such. Lately, if you're using stated screeners and you find that values that are falling beyond 1.5 times the inner quartile range are not the same as what other people are finding, that's just because that program is doing it right. I'm not sure what SPSS is doing with this, but you don't have to worry about that and go through and try and sort of look at your in the Explorer, the different percentile ranges. Just go ahead and interpret it as such. Outliers in SPSS indicated as points extended beyond the whiskers. Anything 1.5 times the inner quartile range will show up as an individual point. In SPSS, extreme values, more than 3 times the inner quartile range, going to be indicated with an asterisk. so remember that if I have a normal distribution, I should expect about 95% of the data to fall between the upper and lower whisker in there. Or how to interpret those. All right. What do we do? We find a univariate outlier. What do we do? How do we address this? If it's an error, just fix the error, right? And again, remember this is going to be if we have outliers or extreme values in either our dichotomous variables or our dichotomous outcomes or our continuous outcomes. Is this a problematic variable, right? Let's say I went through and I'm like, oh, I'm going to sort of make up my own measure of this thing because it's just a kind of on the fly thing and it's just a one-item measure of something. And then I look at it and it's just got a nasty distribution. It didn't turn out what I wanted. Like, yikes. Maybe this is problematic. I need to have a better assessment for this. So this was ill-conceived, I guess, sort of the last-minute thing on my point. Maybe this is problematic and I can't use it, right? Maybe I wanted to capture some of this. Often happens with some of our categorical variables, the demographic types of things. Like, oh, I'm going to measure this. I want to make sure I can control for that in the model, but then I just don't get enough people to give any sort of variability. Crazy uneven splits or small cell categories and things along those lines. Maybe I just can't use this in the set just because I didn't have enough representation in there, right? So think about problematic variables. For outliers, case not representative of the population of interest, right? If the 60-year-old engineer with his six-figure income is not a member of my population of interest, and just get rid of that person, that has no impact on generalizability because I wasn't interested in 60-year-old engineers with six-figure incomes, right? They weren't part of what I was looking for. Just kick that person out. That's not a problem at all. But wanting to make sure that you've gone through, taken a look through your records to take a look. And this is starts to become important where, you know, if you have hard copies or other types of things, to be able to go through and figure out what actually happened with this, so we can maybe figure out what happened. Or maybe it was you know, an RA, so they just kind of did their own thing when they shouldn't be doing their own thing, and you got a bunch of weird scores. Wanted to go through and take a look and make sure that it wasn't something strange. And if it is, you can sort of just get rid of that. It's not a big issue. Or equipment failure, everything went down, right? So you got a bunch of weird stuff that doesn't make any sense. That was a failed participation run. We'll just get that person and get rid of them. And clinical stuff, right? This is someone came in with like an intense personality disorder, and so I have, or someone's coming in and sort of malingering, or I'm questioning the veracity of reporting, or things along these lines, right? Say, is this, or someone comes in with a head injury or maybe a psychotic disorder or something like that. None of their stuff makes sense. Go ahead and get rid of that without sort of general loss of generalizability here. But if it is a person who's a member of your population of interest, right, and their value does make sense, but it also is going to have an impact on your estimates because it's a really huge outlying value, but you don't want to throw them out because these are actually the people that you're really kind of interested in. I'm thinking, okay, a lot of substance use stuff is like this, right? You throw out all your outliers, you can throw out all your people who are using substances, right? And so what do I do then? Maybe I don't have a super high sample of people who are using sort of stimulants recreationally, right? But I've got one person in there in this small subgroup. Some people that I go sort of once or twice a month, I'll sort of, you know, take one of my roommates, Ritalin or something like that, and then you got someone who's doing it like multiple times a day, right? That person's important, but they're going to drag that way out. We need to figure out what we do with that. So one thing you can do, if you've got maybe one or two cases like that, everything else is looking fine, but you got one or two cases that are sort of extreme, right? These are going to be cases where you've got, so here's my distribution, then I've got boom and boom, people who are kind of disconnected from the rest of the distribution, kind of out there. What we can think about is a smoothing procedure. What we're going to do is we're going to take that person's value, we're going to set it to 1 unit larger than the next highest score. okay? So if I've got a scale where the substance use scale, let's say someone's, I've got a value of 15 and 20, right? But my sort of next highest value is an 8, right? I might take the 15, set it to 9, 20, set it to 10. Those individuals still rank order are the most severe cases in the set, but what we've done is we've just taken those scores, smoothed it to kind of reduce sort of the fact that they're sort of way out there and going to drag the whole mean out to the end. This feels a little weird because it feels like I'm making up data and I'm sort of changing things. But again, if I've got a distribution that otherwise looks acceptable and I've just got a couple people who are pretty intense and they're going to cause a problem in terms of my estimation, smoothing is a reasonable procedure to just kind of bring those in, still maintaining the rank order, but when we bring those in, that's going to sort of reduce the overall impact on my estimates. Okay, does this make some sense? Okay, so smoothing. If I'm thinking about when do I smooth, is when I've got maybe a handful of cases, not a lot, a handful of cases, and these are generally like true outliers. Things are kind of sitting out there. Otherwise, the distribution looks pretty good. Right? My other option is I can transform. Then I'm taking a distribution that's fine for 98% of the people, and then I've turned it into something that's not what I originally measured. Now it's complicated interpretations and things like that, just for 2 people that. And I don't want to throw them out because those are people I'm interested in. I just need to sort of get them in line so that it doesn't cause problems for my model. So this would be a smoothing procedure.
So this example you gave the basketball player would be when you smooth, because she is part of the population of interest, but the other bar out there.
Yep, I would, yeah, so say the next tallest person was in my sample was 6'5", right? I would say, well, we'll set this person at 6'6", and just kind of call it good with that. They're still the tallest person in the sample, it's just they're not going to drag things way the hell out there. Okay. Other option is to transform, okay? Transforming is going to be, we're going to go through and apply some nonlinear transformation to the data to change the shape, okay? If I divide all the scores by a constant, does that change the shape? Nope. If I add a score or subtract a score to all the scores, did that change the shape? No. But if I take all scores and change it to the power of 2, does that change the shape? Yeah, that will, right? That's a power transformation or square root transformation. Some nonlinear transformation that goes through and changes the shape of the distribution. Okay? If I've got something, let's say, again, Kate, just because your area sort of has a lot of this stuff, like an audit score or something like that, where most people are kind of down here, have a couple things to do, some people who don't drink at all, then you got people who are drinking a whole lot, starting to skew that distribution way out, right? That might not be something I can fix by smoothing, because we got a big continuous tail that just drags all this out here, right? So what I might want to do is smoothing is going to be helpful because it's I can keep doing it. It's just going to maintain this ugly distribution. What I might do is say within this, within the context of this, I'm going to go through and transform. Experimental folks, if anybody done any like reaction time types of paradigms? Reaction time paradigms are classic for this type of thing, right? So you have most people pretty quick, but then as you start getting sort of slower and slower, it starts to drag. You're sort of bounded at 0. Like your reaction time can't be negative, right? Human processing only goes so fast, but you can get really long out there, right? And so this might be a situation where if you've got maybe 1 or 2 cases who, typically with the reaction time, if someone goes past a certain time, you just cut it off and throw that person out because they weren't paying attention or something like that. But typically what you see with the reaction time data is large positives. You can have a pretty decent positive skew to that. This might be within reaction time literature. Almost always see a transform. That's just kind of what you do, and it would maybe be odd if you didn't transform. Same thing with substance use. Sometimes this is a log transform of this, because we assume it's going to be a nasty have a nasty distribution anyway. Everybody does it. It's not a weird thing to see it. So people see kind of the difference we would take maybe in consideration between smoothing and transformation. Okay. So again, this is the thing, before we decide to address, take a look at multivariate outliers, want to take care of your univariate outliers first. Like if these are your data and you want to go through, because otherwise, if you have a bunch of univariate outliers and you start looking at multivariate outliers, what's going to happen? Because the univariate outliers, you can pop up with multivariate outliers as well, right? So as you're working through your own data, want to take a look at your distributions, want to address this stuff first before you go on and start exploring multivariate outliers. So, some conceptual things to think about with transformations. People love transformations because they think they're fancy. They're actually kind of a pain. You should only use them when you need to. Basically, the big problem with transformation, it complicates interpretation of your data. Okay? If I'm measuring X and then I transform that, I'm no longer talking about X. I'm talking about the transformed version of X, right? So if I go through and I'm looking at measured X and I measure Y, but then I decide Y has a ugly distribution and I log transform Y, I'm not talking about X and Y anymore. I'm talking about X and log Y. And so when I run these analyses, I look at the association of X and log Y. The log Y probably doesn't mean much of anything to anybody. If I'm talking about an audit score, it's an alcohol screening use disorder test, right? I know what an audit score means. I don't know what the log of audit means. And so all of a sudden I've ruined my sort of intuitive interpretation of this variable. Now if I need to do it for the purpose of running my analyses, then it is what it is. But if I don't need to do it, it complicates a whole lot of stuff when I didn't need to. But what happens sometimes, people will log transform something or transform a variable and then just talk about it as if they hadn't done it, and talk about it if it's the exact same. Like, oh, this is how X relates to Y. Like, nope, that's not how X relates to Y. That's how X relates to the log of Y. And now it's incumbent on you to make sure that everybody knows that you're talking about the log of Y and not the actual income. So they think about, there's a nice thing about income, right? Or Evelina, weight, right? I'm talking about weight. I know what weight is. I know what differences in weight is. I know what a large weight is. I know what a small weight is. But if we log transform weight, all that's out the window, right? Now that variable no longer has intuitive value to me, and so now I have to deal with that. So transformation, sometimes necessary, common practices. Alcohol or substance use, alcohol substance use disorders is pretty typical. People doing reaction time stuff, pretty typical. In some areas, this is just the data that we work with behave this way, and this is what we need to do in order to deal with it, and so it's not a big deal. For people in those areas, maybe the log transform or whatever that variable is makes a lot of sense because you just see it all the time, right? But what you shouldn't be doing is conducting transformations unless you have a good reason to do so. Okay? There's another thing, again, I had said before, reviewing papers, and people say, well, I had significant skew, and so I log transformed sort of whatever variable I had. Wait, no, let's talk about what you're significant, because it doesn't seem like you should have problematic skew in these data. Like, oh, well, my significance value for skew was 0.012, and so I transformed everything. Like, no, don't do that. That's going to be fine. You just complicated your interpretation a whole lot, right? So if you want to do it, you want to make sure that you have a good reason to do it, because the level of skew that you're seeing, or the non-normality you're seeing in your data is problematic, and running these analyses in the absence of doing something with this is not going to be reasonable. So, Tabacci and Fidel talk about Tabacci and Fidel advocate for pretty liberal use of transformation. I'm going to say, do it if you need to, have a good reason for it, but know that it's not a free lunch, right? I can't just transform stuff and then it's fine and it's like my data were normal the whole time. It comes with a cost and starts to impact interpretability. Now, there are certain types of transforms that we can use that are better, that lend themselves to some nice interpretations, but in general, know that if you transform variables, it's going to create additional burden for you in terms of interpretation. All right, so common transformations: moderate positive skew, square root of x, large positive skew, the natural log of x. If you got a large positive skew with 0 values in your data, you're going to have it take the natural log of x plus some constant. why do we need to add some constant to, if we're gonna log transform something with zeros in it?
Does it make it 1?
Yeah, right. What happens if I try and take the log of 0?
You get 1 value, or it equals 1, right? For 10.
Take the log of 0?
0.
It's undefined. It won't give you an answer. It'll say error, right? So you can't take the log of 0. So if I have a, say, a 0 to 8 scale, what I'm going to do is I'm going to just take and add a constant of 1 to every value, right? And so now my scale isn't 0 to 8, it's 1 to 9, right? And so now I can take the natural log of that, right? I'm screwing with the scale anyway, so who the hell cares what the scale is, right? Just going through and making sure that I can do it. If you try, and this will happen, you'll try and log transform something, but you'll have 0 values, and then you come up with a bunch of missing data in there. It's just because it can't perform a calculation. You can't take the log of 0. Sort of like dividing by 0. You can't do that. Yeah.
Never mind.
Got it?
Yeah.
Haley's checking. She's like, what happens?
She is.
It'll make your calculator blow up. That's what happens.
Yeah, it says error.
Yeah, yeah. So because the log of 0 is not defined, and so it won't actually give you a value. So if you have 0 values in there, or if you have negative values, right? Let's say your scale range is -4 to 4, right? What would we want? What constant would we add to that variable in order to be able to log transform that?
You said you can't do negative values?
You can take log of negative value.
Oh.
I think. Try that.
You can't do the natural log. I don't know about regular.
Oh,
log.
then yeah, regular is just a different basis. That'll be fine. Okay. So yeah, with negative values, so I got a scale ranging -4 to 4. What's the constant I need to add? There's an infinite number of constants I could add. What would make the most sense? 5. Yeah. Because if I add 5 to all my variables, my lowest -4 is now a value of 1. 4 is now a 9, right? And so basically, we just need to get all those into positive integers. Okay. Severe positive skew. This is x to -1, so you take all values in the -1, right? This is an inverse. This is an inverse transform. X to the -1 equals 1 over x, right? So you're just taking so the reciprocal of those. When we get into also same thing here, if you've got 0 values, you can't take 1 divided by 0, right? So you have to go through, add a constant. So these are all for variables with positive skew. If we have negative skew, then we've got a whole new type of thing. We have to get into some reflection business, because if you have a negative skew and you log transform the negative skew, it's just going to make the negative skew worse. And so what we need to do is take these negative skewed values, we need to reflect them, turn them around, so negatives, positive, positive, negative, and then go through and do some of the same transforms that we've got. So we've got something that, okay, this is a good example. So in our assessment project, we administer SF36. Anybody familiar with SF36? It's a health questionnaire, the World Health Organization health questionnaire. But we're working with as different scales looking at like health data, pain, and sort of physical functioning type of stuff. Because we're working with undergraduates, what's the physical functioning and health of most undergraduates? Pretty good, right? If we're working with like survivors of motor vehicle accidents, then it's not great, right? But what we end up is 100 is great health, 0 is terrible health. And so in our data, we've got a strong negative skew to those data, right? Because most people are doing good. We've got a couple of people who aren't doing so great, but we've got a strong negative skew there. And so what we would want to do if we needed to transform that, what I would need to do is create a counter reflection. So what I would need to do is get a constant that I subtract from each score. K usually set to equal the largest score of the distribution plus 1, right? So if I have so if this is a 0 to 100 scale for the SF36, right? What I would do is I would take every score in that set and take 101 minus people's values, okay? So So if I have 101 minus my top value is 100, what's that score now? It's 101 minus 101, right? So all my people in good health who had scores of 100 now have scores of 51, right? Yeah. And so to go through, so what I've done is I've taken that variable and I've reflected it. So now that the high values mean low scores and the low scores mean high scores, and so I've created a new variable with the reflection that now has a positive skew. And then what I can do is I can transform that positive skew and get it sort of normal. But you can see in this case, now what I have to do is now my positive associations mean that the relation with the construct is actually negative, right? See what I'm saying? So now if I have up is down, down is up, right? So if I see positive, so what I need to do is keep track of what these variables actually mean. And so if I reflect it, that means that a positive relation actually means an inverse relation. As my one construct goes up, my other one actually goes down, even though the numbers are going up because I reflected it. And then I also have to account for the fact that I then took that reflected scale and I transformed it. You can see how this starts to get messy in terms of just communicating what's going on in your data to other people, right? So again, I've become more open to transforms and their potential, particularly with some different transforms that we can use that maintain some level of interpretability, but still wanting to recognize that if you transform data, it's incumbent on you to acknowledge and talk about it as a transform variable, not just as the variable you want to measure in the first place. Yeah.
How would that interpretation differ?
What's that?
How would the interpretation differ?
Kind of depends on what you want to do, right? So if I want to say, so this is the relation between x and the log transform of y. So now I don't talk about y, I talk about the log transform of y. That's just kind of my standard vernacular. Now if I wanted to go through and say, this is the relation between x and the log transform of y, and then you get some predicted value, right? What I can then do is back transform that into an actual value that I can say sort of talking about some stuff like that, but you kind of have to be careful with how you go through and do that and whether or not it makes sense. What's nice is our natural log transform here within the context of a regression maintains interpretive properties. So if I, instead of in a normal regression model, I can say as variable x increases, y increases by this much, right? What I can start doing is saying as with every unit increase in x, we get an x% change in y, right? Or as we get an x% change in x, some percent change in x, we get a corresponding unit increase in y. Or if we transform both of them, we can say a 1% increase in x results in an x% increase in y, right? And so this maintains some interpretive value because I can think about percentage increases in x, even though that's not a sort of unit to unit increase. And so this is where if you're going to go through and use transforms, the natural log is a nice one to use because at least within the context of regression, it still maintains some of those advantageous interpretive properties. And we'll get into that a little bit more when we get into some of those regression models. Yes?
Sorry.
No.
Does transforming compromise validity at all?
No. Well, you're not talking about the variable that you were originally talking about, right? You're talking about a nonlinear transform of that variable, right? But for sometimes, like that's the best we can do because our other option is to not transform and to get stuff that doesn't make any sense in terms of things that we can have confidence in. So it just makes it just puts more burden on you to make sure that you know what you're talking about and being able to describe it appropriately as you move forward with stuff. Other questions? All right. So when we're interpreting our transform data, with our ungrouped data, right? We're talking about regressions and things along those lines. Our observed associations, we're interpreting these as associations with the transform variable, right? This is a relation of x and the transform variable y, right? This is an association of extroversion and the log of regression scores, right? Now, the log of regression scores doesn't mean anything to anybody, right? But that's what we've done, so we have to describe it appropriately, okay? Now, with group-based data, if we're looking at t-tests, right? So I have a problem where my outcome is I'm looking at, going back, Kate, I'm looking at gender differences in audit scores or something like that. And I've had to transform those audit scores. Or I'm looking at class year in college, sort of junior, sophomore, freshman, senior, and looking at alcohol use on the audit, right? So I've gone through, my scores are really skewed. So I've gone through and I've log transformed that audit in a means-based test with our t-test, our ANOVAs, realizing that now that t-test is talking about the difference in medians as opposed to the difference in means. Okay? When we go through and we transform our data, transform changes the shape of the distribution but not the order of scores. Okay? So in my audit score, which is nasty EE as a nasty distribution, right? And it's sort of like this. If this is my median score, remember, and this is Phil. Phil's at the median, right? Phil has a score that is at the median of my untransformed audit, right? When I go through and I transform, I log transform that, my transform score, my transform distribution looks better. Maybe it looks something like this. Phil's still at the median, right? The middle score of your transform data is still the middle score of your untransformed data, right? And so when we're talking about differences, mean differences in our transform data, the person at the middle of the distribution, the center of the distribution, literally the person who has sort of half the scores above and half the scores below is still in that same position in the transform scores. So our transform doesn't change the order, the rank order of individuals, right? The rank order of individuals in terms of whatever it is we're measuring stays the same. It's just kind of the differences between them start to get changed with the nonlinear transform, right? So this is, I've managed to work, I like that I get polyandrous live-bearing fish in this. Again, it's fun things to pull up on Google, right? But what we've got here is some untransformed data, right? And so we've got, again, for this study on ecology and evolution, we're seeing sort of whatever it is that we're measuring has kind of a skew that they're finding to be problematic, okay? And when we transform that data, this isn't a great distribution. There's some gaps going on in there, right? But what it does is it takes all these values and sort of brings them in, right? And so the lower values kind of brings them out. So it's something that's much more acceptable. But the case that, what do we say, this case, is this the median of this distribution maybe? Let's say it is, right? The person who's at this case, cases that are at this value, the median of my untransformed variable, they're also at the median of my transformed variable. So when we're talking about means-based analyses or group-based analyses, normally what we're doing is we're talking about differences in means. As soon as we're using transform data, we're talking about differences in median differences across this group and that group. Okay. So again, just wanted to make sure that you're talking about this correctly as you're going through and running these analyses. I mean, you're talking about the mean of the transform score, certainly, but what we're really talking about, the mean of the transform score, we're really talking about sort of median values and how those shift around. Questions with transform stuff? All right. Multivariate outliers. How are we going to go through and identify these? Because we've got a kind of a difficult situation where we've got values, cases that can have on individual variables be reasonable, but put together they're not reasonable. Okay. What we're going to do for our general multivariate screening is calculate a Mulholland-Novus distance. Okay. And Mulholland-Novus distance, or Mulholland-Novus distance, is distance of a case from the centroid of the remaining samples. So now if we're thinking about multivariate space, centroid is like the mean of the intersection of all means for all your variables in your analyses. Okay, so let's say again, three-dimensional world here. So throw the sort of thumb and forefinger, create your axis here, right? So if we've got height and weight, right? On here we can choose a point that's height and weight, and here's the mean of my. If I take the mean of height and the mean of weight, it's a point right here, right? But then if I say add a third variable, if we add a third variable, then we'll go into three-dimensional space, right? And so let's say I include age. Some here in three-dimensional space is the intersection of the mean of height, the mean of weight, and the mean of age, and that's my centroid. That's where that sort of value is laying. What we're looking with the Malholm-Novus distance is where this person's intersection of height, weight, and age falls relative to sort of the index of the mean height, mean age, mean wage of everybody else, of the rest of the sample. So in this case, if we're looking at height and weight, case 232 has a height of, say, and so in a two-dimensional space, right, we've got height of 60, weight of 220. Here's my centroid. Here's average weight, or average height is, looks like 68 inches, and average weight is 180, okay? So this is the mean of my sample mean of height, my sample mean of weight. Here's the centroid in that two-dimension space. Okay. Then I've got someone who's has a height of 60 inches and a weight of 220. Okay. This person may end up registering as a multivariate outlier because of the distance away from sort of the clustering of everyone else. Okay. So this is pretty easy to see in two-dimensional space, but if we add a third variable, right? So this person, in and of themselves, 220 is 40 pounds above, but it's probably not. I probably have people who are equally as heavy, right, in the sample. So 220 itself might be high, but it's not going to be terribly high. And 60 inches is small, but it's probably not terribly small, right? But you add those two things together, and all of a sudden in multivariate space, it's a distance that's far away from the clustering of the rest, okay? Same thing. Let's say if we add in a third variable, right? We go, we have height is 76 inches, that's tall, right? But not maybe abnormally tall. Weight 230, that's heavy, but not maybe abnormally heavy. Then let's say we look at sex. What's going to turn this into an immediate multivariate outlier? If it's a woman, right? If it's a guy who's 76 inches and 230 pounds, where I was several years ago, I'm no longer there, right? But if I'm male, I'm above average, but I'm probably not abnormal. I'm a freak, right, hanging out there. But if you had a woman who was my height and my weight, she would be a freak. She would just be a very, very large woman, right? And someone who would not be characteristic of the rest of the other people in my sample, right? And so I'm glad this is all recorded, so that goes on to YouTube. I'm trying to say is that sort of we start to see people with characteristics that are not typical of the rest of our sample, and so so this might be an outlier, but as soon as I sort of throw in a third variable, now all of a sudden we've got a case that's way off base of what we'd expect from the rest of the sample. Okay, kind of see how the idea behind the Malholm-Novus distance and how that's working out. Okay, magnitude of Malholm-Novus distance. What's nice is we can kind of get a sense for how big this value is. Malholm-Novus distance has a distribution based on chi-square distribution, with chi-square degrees of freedom equal to number of predictions or number of predictors. So what I can do is I can take the Malholm-Novus distance that I've obtained and compare it to a critical value with the number of degrees of freedom equal to the number of predictors to try and get a sense for sort of how extreme is this given sort of what we've got in our data. Malholm-Novus distance that exceed chi-square degrees of freedom for a critical value less than p less than 0.001. Tabashik Fidel identified this as a very conservative estimate for what constitutes a multivariate outlier, saying that it's pretty conservative. We're keeping the range pretty tight on this, right? But this is kind of something that you can, a basis that you can use to take a look at this. All right. So let's say we've questions on multivariate outliers and what those are, and sort of thinking about how those might turn up in our data. Okay. So we've identified a case as a multivariate outlier. The battle is half won, okay? What we now need to do is describe and figure out why that case is a multivariate outlier. What about this case, what about this pattern of scores is causing it to look not normal relative to, or atypical relative to the rest of the sample? We want to do this and sort of make sure we're in the example, or in the example of the walkthrough we do in class, we'll sort of go through procedures, identify sort of what specific variables are causing this to register as a multivariate outlier. But important because, one, it's going to help us identify variables that are potentially problematic. If I've got, say, if I identify 4 multivariate outliers, and they're all multivariate outliers because of scores on the same variable, that starts to suggest I might have a problem with that variable. That might be something I need to think about. It helps me decide whether or not the case is part of an intended population, whether or not I should retain it, right? Honey Boo Boo example, Honey Boo probably wasn't a member of my intended population, right? That's someone who is unique in a number of different ways, and so maybe we go through and say, no, this person is not part of who I'm trying to generalize to, so we get rid of that. Also helps to give us a sense for what types of individuals does our model not do a nice job accounting for, right? If I have a handful of cases I've identified as multivariate outliers, and they all kind of have the same characteristics that are causing them to become multivariate outliers, I can say, okay, what I've got is I've got a model that does a pretty good job of accounting for whatever it is that I'm trying to account for, except for these group of people. If I'm talking about this subset of the population, this model doesn't do a good job of addressing sort of these types of things, right? And so this starts to become important because it starts to help me sort of narrow in on who I can generalize these results to and who I can't, right? So if I find a bunch of cases that were theoretically, conceptually important, but in my data end up being strange multivariate outliers because of strange patterning of the combination, right? Then I might say, okay, so these are people who this model doesn't do a nice job of accounting for. We go through, use our regression analyses to determine sort of what variables are causing variables cases to be multivariate outliers. So once we've identified them, we can use some regression techniques to go through and tease apart what specific cases are causing these individuals to come up as problematic. But we'll go into that when we actually do the walkthrough in SPSS. So addressing our multivariate outliers, get rid of them. Okay, you got a case that's a clear multivariate outlier, you delete it, right? The problem is even if it's someone that you're interested in, that's someone who's, we're going to talk about influential values and things along those lines. We're just going to get rid of them, sort of note them, and identify what characteristics cause them to register as multivariate outliers, and then we're going to get rid of them. What ends up happening is that these multivariate outliers can have an unpredictable impact on your model, and often you can have maybe entire effects that are dependent on 1 or 2 people in your sample. That's not a good thing, right? And so with the multivariate outliers, you're just going to identify them. We're going to go through, walk through some graphical methods to try and sort of get a sense for to what extent are these people sort of way out of balance. And then once we've identified them, we're just going to say we've dropped them out of the thing because they can have serious impacts, and it's difficult to predict. Some stuff you can say, oh, this will make my standard error too big, my standard error too small. Multivariate outliers, who knows? Right? Really tough to tell. Other thing to be thinking about in terms of trying to address outliers, this can be just an exhausting task, right? So I find an outlier, like, there's my outlier, and so what I'm going to do is I'm going to go through and I'm going to smooth that down, right? So I go through and I smooth it, and then look at my smooth distribution. Now things that were kind of extreme are now really extreme in the smooth distribution, and so now I've got to do something with that. So go through and take a look at it again, and it's just an endless type of situation. So if you're going through, run some initial things. I go through the smooth or maybe transform or something like that. What you can do is, if it looks like it's just gonna be sort of a thing and a thing, and then now all of a sudden I've sort of changed the values of half my data because I'm trying to get the whole thing drugged in and stuff like that. Go through, and once you've figured out what you've done and decided to do, run the analyses with your modified data and in the original set, and see if you can get a big difference talking about, right? If you do get a big difference, then you got to go with the thing that's adhering more to the assumptions of your test. Is going to be the smooth or transform data. You might be tempted to use the untransformed stuff. Don't do that, you know. But you can go through and use that as a way to compare. Does this have a big impact on your coefficients? Oftentimes it won't, right? And if that's the case, then just say, hey, went through, did some stuff. Results with the transform, the untransformed were functionally identical. So we're just presenting the untransformed data just because it's going to be easier to talk about. Okay. If you go through and have done some stuff, and I've gone through and I've smoothed, and I've still got a skew that's not great but acceptable, leave it alone. Don't smooth your data and then decide to transform the smooth data that turns into a mess. Right? If you've gone through and if it's workable, even if it's not perfect, just leave it alone. Go forward with it. We'll talk about linearity assumptions. Just kind of review, we've talked about this before. Linearity are analyses, right? General linear model is assuming linear relations between different variables, combination of variables. We're saying that a straight line adequately represents the way in which x and y are associated with one another. We're going to diagnose this through our bivariate plots for the most part. We're just going to scatter plot x and y, different combinations. But in cases where you have lots and lots and lots of variables, let's say I've got a regression model with 20 predictors in it. I don't know why you would do that. At least in our field, that would be kind of weird. Other fields, that might be something that would happen, right? It would be, if you've got 20 variables, looking at all possible bivariate plots between 20 variables would be quite a chore. Your knowledge, theoretical conceptual knowledge of these variables and sort of some of the evidence for non-normal distributions might start to guide what specific plots you go through and take a look at, right? So if I've got a regression model with 20 variables in it, all possible pairwise is a lot to go through. And I might say, I know that this variable, I've got an audit in there, and that's got a nasty skew. I'm going to want to go through and make sure and take a look at other predictors with audit specifically to go through and see if I've got any non-normality. Or I know that from a theoretical standpoint, the relation between x and y has been, people have suggested this may not be, this may be nonlinear. So I want to go through in my data and see whether or not a straight line is a reasonable fit for the data, given that there's evidence of some nonlinearity with this outcome. Okay. Linearity starts to become super important. Again, our multivariate assumption of multivariate normality is assuming that each variable, all possible linear combination of variables, are normally distributed. We're assuming that sort of everything that, in order to sort of make the general assumption of multivariate normality, we need to make sure that these individual bivariate relations are linear and homoscedastic, right? So if I go through and I find evidence of something like this, right? I've got a clear nonlinearity there, right? That's going to go through. If I estimate this with a linear equation, what is this going to do to my estimate of the relation between x and y? It's going to decrease the magnitude. It's not going to be it'll be an all right fit, and a line might actually be a reasonable fit for this, right? But it's not going to be as good a fit as if I had a quadratic or something like that in there that contains a nonlinear function, right? So sometimes I have to decide, is the additional complexity of this model worth sort of going through and sort of capturing sort of the nonlinearity in there? And sometimes it's not. Sometimes we default to parsimony and just say, well, it looks like it's possible that this could be nonlinear, but we're just going to estimate it as linear. That's going to be good enough, right? But if you have theoretical reason to believe that this relation is not linear, that might then be an important thing to think about in terms of, do we start to model nonlinear relations? If you have something like this, right? Yikes, right? I can't, right? The linear relation between x and y, it's going to say there is no relation between x and y, but there's very clearly a relation between x and y. It's not nonlinear, right? So we need to go through and address this. Here's another example of something that has some sort of negative quadratic. Again, we could estimate it a linear thing, but we're going to miss a lot of the stuff going on in there, right? So our options, we can transform, and this is probably what we do most often, and this is what, if you see nonlinearity, some sort of transform. If I take this variable and I square y, that's going to make that almost a perfect linear relation, right? Because that's squared, that we're seeing a sort of quadratic here. So if I take the square of y, then that's going to address this issue, right? Then I'm talking about the relation in the square of y. So that's going to take care. One of the things I can do also is dummy code some different piecewise analyses, right? Or excuse me, dummy code. If I want to say, look at, let's say I've got this variable here, right? What I might say is at 0, down is 0, here, up, that's 1, right? It's not a great solution, but what it's going to do is it's going to say at low levels, y is low, at high levels, y is high. That will capture some of that relation in there. I can also run some piecewise analyses, right? So I'm running a piecewise model maybe for this, although this is an easy transform, that fixes that pretty easy. But what I could do is I could say I'm going to run a model for the relation of x and y from -5 to 0, the relation of x and y from 0 to 5. This is going to be a clear positive relation, right? If I cut this in half, I got a nice linear relation here, and then here I've got a nice negative linear relation here. And so we're saying the relation between x and y between these bounds of x is positive. The relation between x and y and these bounds is negative. Some different types of things we can do there. Nonlinear analyses, we can start to run different types of models that include power terms and things along those lines, or we can also ignore it. Right? This example right here might be a case where we might just ignore it, right? Because in these data, it might look like I can see what looks to be a nonlinear trend in these data, right? But if I don't have a theoretical reason to believe that these, the relation between these variables is nonlinear, this could easily just be an artifact of the sample that I've collected. And if I'm not willing to go stick my neck out and say no, in the population association between x and y is best captured by a nonlinear function, my linear model will capture most of that. It won't be maybe as good as a nonlinear, but what I'm worried about is capitalizing on sample-specific characteristics. When I'm saying, oh, for these data, it's nonlinear, when it's actually in real life, if I were to get a bigger sample, it would be clearly linear. It's just for these data, it looks like it might have a little bit of an acceleration going on, right? And so if we do that and decide that the added variability that we're accounting for with the nonlinear term isn't worth the added complexity of the model, we'll just say, probably not on the screen, it looks like it's probably, could be a nonlinear one. We'll take a look into this a little bit more, but we're just going to ignore and proceed with our linear model. All right, questions with this? All right, cool. We're getting close to being done. What do we got? Variance assumptions, multicollinearity. Okay, cool. We'll pick up there on Wednesday and make it through our